physical picture of the divergence. Let's say that we have a small box which has sides dy, dz, and dx, and we're looking at the number of particles that are entering and leaving this box, and the particles are approaching with velocity vz at position x0, y0, z0, and leaving at z0 plus dz with velocity vz at that point. And we're going to call the number of particles per unit volume, the number density, as rho. Rho is a function of position, x, y, z, and time, t. And we call the velocity of the particles at position x, y, z, and time t, the average velocity of the particles, v bar x, y, z, and t. So it's both space and time dependent. Now, what is this differential volume that is defined by the dimensions of this box, which is positioned at x0, y0, z0 here? That volume is d tau, which is dx, dy, dz, the product of the side lengths. Okay. And we have a number of particles that are entering and leaving, but particles cannot be created or destroyed within d tau. So this is our condition. So if I call capital N is the total number of particles in d tau. This is going to be N is equal to number of particles per unit volume rho multiplied by my differential volume d tau. Okay? So that's the total number of particles in this volume. Now, if the total number of particles in this volume is changing in time, then I can look at the rate of change of the number of particles, total number of particles in the volume, the partial derivative of n with respect to time t. Now, since it depends on the volume d tau and it depends on the number density, so the volume is constant. Therefore, I'm taking a derivative of the number density at position x, y, z at time t with respect to time, the rate of change of number density, and this is evaluated at the position of the box x0, y0, z0 at time t multiplied by the volume of the box dx, dy, and dz. All right. Now I'm concentrating on the number of particles that are entering this box from the bottom and leaving this box from the top. So if I look at the total number of particles that enter volume d tau from the bottom surface, that's going to be the number density at x0, y0, z0 at time t multiplied by dx, dy, and the value of the velocity at that point, x0, y0, z0, and the volume is the velocity multiplied by dt, so that's going to give me this side length, dx, dy, vz, dt will give me this volume. So volume multiplied by the number will give me the number of particles that enter from the bottom surface. So this is the number density rho at x0, y0, z0 at time t multiplied by the volume dx, dy, and vz evaluated at x0, y0, z0 at time t multiplied by dt. So this is the change in the total number of particles due to the particles entering this region from the bottom surface. All right. So Now, if this number is changing in time, so we're looking at the contributions from the bottom and top here. The change in the number of particles entering from the bottom surface, del n del t, the time derivative, will be equal to the number density rho at x0, y0, z0 at time t, dx, dy. So let's write Vz here. Vz multiplied with, so its value at x0, y0, z0, dx, dy. So we've taken dt to this side. Okay. Now I call the current density J bar, and the current density is the number density multiplied by the average speed. So it's the number of particles per area per unit time. It's called particle flux. Okay, so a number of particles per unit volume multiplied by velocity. So we have number of particles per area per unit time that are crossing from the bottom, in which case we can write the rate of change of the number of particles from the for the particles entering from the bottom surface, del n bottom del t, can be written as the value of the particle flux Jz evaluated at the bottom surface x0, y0, z0 at time t multiplied by dx dy. So we have replaced rho times Vz with Jz, which is our particle flux. And if I repeat this exercise for the top surface, so let's think for a moment how this result would change. So we would have the partial derivative of the number of particles leaving from the top, del t. Because they're leaving, the particle flux will be negative, so it's minus Jz. Now this particle flux is evaluated at x0, y0 and z0 plus dz, okay, and dx dy, and the minus sign implies that the particles are leaving. So you can see here we have the velocity evaluated at c0 plus dz multiplied by rho in this volume, which gives us the flux that is leaving this top surface. So we put a minus sign to indicate that they are leaving. Okay, then what is the net change in the number of particles at the differential volume? Delta n is due to the number of particles that are entering from the bottom plus the number of particles that are entering from the top, which is negative because they are leaving. So with that, we can write the net change in the number of particles, del n del t, inside this differential volume to be the partial derivative of the number of particles entering from the bottom with respect to time, del n bottom del t, plus the partial derivative for the number of particles entering from the top, del n top del t, which is negative because they're leaving. So this is going to be the difference in the fluxes, particle fluxes, or the current densities between the top and bottom surfaces. So Jz evaluated at x0, y0, z0 at time t, that's due to the bottom surface, and minus Jz evaluated at x0, y0, z0 plus dz at time t from the top surface multiplied by dx dy. dx dy. Okay. Now, let's multiply this with delta z and divide it by delta z. In the limit delta z goes to 0, it will become dz. So if you look at this difference here divided by delta z, in the limit delta z goes to 0, that's the derivative of the particle flux jz with respect to z. So this is, by definition, the limit delta z goes to 0, jz evaluated at x0, y0, z0 plus delta z t minus jz evaluated at x0, y0, z0 and time t divided by delta z in the limit delta z goes to 0. So you can see that we have the minus version of this here. So for that reason, we can write for del n del t, del n del t is minus the derivative of jz with respect to z, partial derivative with respect to z, which is evaluated at x0, y0, z0, and at time t, multiplied by dx, dy, dz, because delta z has become dz now. Okay. Now we can repeat this procedure for other 4 surfaces, and we can write the total change in the number of particles del n del t to be, including the contributions from all 6 sides, we have minus del jx del x from the side surfaces, minus del jy del y, and also from the top and bottom surfaces, del jz del z. So left, right, top, bottom, front, back surfaces, they're all included in this calculation, and this is to be evaluated at the position of the box x0, y0, z0 multiplied by dx, dy, dz. So now J is related to the number density rho here. So this is rho times V bar. And therefore, we can say that del n del t is, it can also be written as del rho x, y, z, t del t, the derivative with respect to time, del t, evaluated at x0, y0, z0 at time t multiplied by d tau, and there's our, because j is equal to rho v bar here, v bar, this is our vz evaluated at x0, y0, z0. Okay, now if I look at the divergence of J, the particle flux, divergence of J, this is the gradient operator dot product with my particle flux vector Jx Ex hat plus Jy Ey hat plus Jz Ez hat, which is del Jx del x plus del jy del y plus del jz del z. So I can see that here I have the minus the divergence of j multiplied by d tau is equal to del n del t. So I can write for the rate of change of the particles, particle flux density, del rho particle density, number density, del rho del t is equal to minus the divergence of j. Okay, so del n del t is minus the divergence of j times d tau. So basically, there is no vz here because if I divide it by d tau, this just becomes rho. So number per volume. So n divided by dn divided by d tau basically gives me the number density. So del rho del t is equal to minus divergence of j. So if I find that the divergence of j is positive, that means del rho del t will be negative. And that will imply more particles are leaving than entering. So this equation, del rho del t, the rate of change of number density, is equal to minus the divergence of the particle flux minus divergence of j. This is known as the continuity equation. All right. And what it says is if the divergence of a vector field is positive in a region, then that region is a source. It's a source of particles. There are more leaving than entering. So field lines are born within this region. If the divergence of a vector field is negative in a region, then that region is a sink. That means more particles are entering than leaving, and field lines are terminated in this region. And if the divergence of a vector field is 0 in a region, then that means all field lines that enter that region, that enter it, must leave. Okay, so it's not a source of particles or a sink of particles. All the field lines that enter that region must leave. Okay, so let's see what we have done here. We have the number of particles per unit volume, rho, and we have the average velocity of the particles. So Vz is along the plus z direction, evaluated at a position and time. And we have this differential volume d tau dx dy dz. So we have a box situated at x0, y0, z0. Particles cannot be created or destroyed within d tau. So we're assuming that the number of particles that are entering is equal to the number of particles that are leaving, for example. Or there may be more particles entering than leaving, or more particles leaving than entering. So that will be our conclusion. Capital N is the total number of particles in d tau. It's going to be rho times d tau. So rho is, in other words, the derivative of the particles, number of particles per volume. So that del N del V, so that del V is del tau here. So it's the number of particles per volume. Okay, so if I look at del N del T, the number of particles within this region, differential region, the rate of change in the number of particles, it is del rho del T times d tau. And the number of particles that enter d tau from the bottom will be the number density rho multiplied by dx dy vz dt. Vz dt is one of the sides here, so that's basically this side here is vz dt, side length. So dx dy vz dt multiplied by rho gives us the number of particles that are entering from the bottom. If I take dt to the right hand side, the change in the number of particles entering from the bottom per unit time is rho times vz dx dy from this equation. All right, and J, the particle flux, is rho times the average speed of the particles. The number of particles per area per time is the particle flux. So we can say that rho times V bar, so rho times Vz in this case, is our particle flux. And we have dx dy multiplied by dx dy, that's del n bottom del t. And similarly for del n top del t, we have minus jz dx dy. Minus sign indicates that we have particles leaving this region. So the change in the number of particles due to the particles entering is delta n bottom, particles leaving is delta n top. So del n del t is del n bottom plus del n top. You can see this is minus jz evaluated at z0 plus d0 dz minus jz evaluated at z0 divided by delta z multiplied by dx dy dz. So we can see the definition of the derivative with respect to z here for the particle flux. That gives us del n del t is minus del jz del z dx dy dz. So if we repeat this procedure for all four sides, we obtain del n del t is minus the divergence of j multiplied by the d tau. So you can see that del n del tau, the number per volume is rho, so it's del rho del t is equal to minus the divergence of j. So we obtain this continuity equation, and it tells us that if the divergence of j is positive, del rho del t is negative. That means more particles leaving than entering. If it's negative, del rho del t is positive. That means more particles entering than leaving. So that means it's a sink. So in the first case, it's a source. In the second case, it's a sink. If del divergence of j is 0, del rho del t is 0, then the number of particles in this region are not changing. That means all field lines that enter it must leave this region. So this tells us the physical meaning of divergence.